Hello, today we'll be talking about Physics 2211, the Lab 3, Black Hole. So a preview of the results of this lab. In this lab, we computationally found the mass of a black hole and determined the velocity of a spaceship that came in contact with this black hole. So a preview of the results is that the mass of the black hole, 1.38 times 10 to the 34th kilograms, with the initial velocity of the spaceship being negative 2.3 E8, 3.0 E70 meters per second in vector format. Some fundamental principles that we have to talk about in order to understand this lab is Newton's second law and the universal gravitational force. On the right, you see the equation for the universal gravitational force. The force of gravity equals G, the constant of gravity, times the two masses of the objects over the magnitude of the distance between them squared, times the negative unit vector between the two objects. For Newton's second law, you see that F net equals the change in momentum over the change in time. Using this, we can find that F net is equal to the perpendicular and parallel components of it. We can also derive to find the velocity update formula and the position update formula, which will be important in order to understand how this lab works. The first part of this lab was to find the mass of the black hole. The system is the black hole, and the surroundings are the star. The initial condition is that the mass of the star is 2.0 times e to the 30 kilograms, and the time is 1 day on Earth, with the observation time starting at t equals 0 seconds. Here's the glow script code for the first part of the lab. As you see in the top left, you see the gravitational constant, the mass, and the delta t, which are the givens. You also see the while loop, which helps determine the change in momentum in order to find the net force, both in the parallel and perpendicular components. And then in the bottom right, we find the mass of the black hole, signified by MBH equals. This way we take the magnitude of the net force times the magnitude of the position of the star, times the magnitude of the position of the star again, divided by the gravitational constant times the mass of the star. And by doing that, we can find the mass of the black hole. After running this code, we come to the conclusion that the mass of the black hole is 1.38 E34 kilograms. F net is 8.97 E28 newtons, with the parallel component being 1.48 and the perpendicular component being 8.847 times e to the 28 newtons for both, respectively. Moving on to part 2, where we find the initial velocity of the spaceship. The system will be the spaceship. The surrounding will be the black hole and the planet. And the initial conditions will be the mass of the black hole, which was taken from the last part of this experiment, which shows that it's 1.38 e to the 34 kilograms. This is the glow script for the second part of this code. On the left, you see the while loop, which finds the force on the ship by figuring out the force of the black hole and the force of the planet both on the ship, and uses those for the velocity update and position update formulas found at the bottom. And on the right, you see we entered the black hole mass from part 1 of the lab. The results of this show that the minimum initial velocity for this spaceship has to be negative 3.7456 E7, 1.9997 E60 meters per second in vector form, with the smallest distance it can be from the black hole being 2.7483 E8 meters. There are some possible sources of error in this code. If we run the program too long, if we do not run the program long enough, we might not get an accurate average mass of the black hole. And that the initial velocity was found through trial and error. There could be other values that would work as well. And this simulation assumes there's no other forces acting on the system. In reality, there are other celestial bodies that affect the net force. What does it mean? Well, net force and parallel perpendicular components are different from the rate of change of the parallel and perpendicular component because they result in the same value, but they're not mathematically the same. The net force requires that you know all the surrounding forces acting on the system. The change in momentum, you only need to know the system's change in velocity and mass. So it's easier to find the change in momentum rather than the change in force, which is why we use that in order to figure out this lab. What if the initial velocity of the spaceship was enough to enter into some kind of orbit around the black hole? Well, using trial and error, we found that the initial velocity must be negative 2 e to the 6, 9.61561 E60 meters per second. Thank you.